Today I'm going to be talking about the epimorphism problem into dihedral groups, or the target groups, which is dihedral. So the epimorphism problem essentially asks, given two groups or two classes of groups, does there exist an epimorphism from the first group to the second group? Some examples that we were interested in is just a finite presented group to a finite group. It's a little nice warm-up exercise. Nilpotent to nilpotent group, which I'll talk about briefly in a bit. Finite presentations to virtually abelian groups, and finite presentations to dihedral groups, which is the focus of this talk. So Remeslennikov showed that nilpotent to nilpotent groups is actually undecidable, which was a very strong result in 1979. This kind of killed a lot of momentum in the area, I suppose, because you can't really look at anything more complicated if nilpotent to nilpotent is already undecidable. We also observed that using a result for equations in free groups, you can show that the epimorphism problem into free groups is decidable. And I'll roughly talk about how the epimorphism problem and equations over a group is very closely related. So more recently, Kuperberg and Samperton, showed that certain fundamental groups, so manifolds, into finite non-abelian simple groups is NP hard. This gives the corollary that epimorphism into finite groups is NP complete, which is a similar result to what we give for dihedral groups. And also Fried and Lowe showed that the epimorphism problem into certain subclasses of virtually abelian groups, not all of virtually abelian groups, is decidable. We expand on their results a little bit. So we show that for these virtually abelian subclasses and slightly more, these are all NP complete. And we showed a different method using dihedral groups of not power of 2 to be NP hard. We also observe a few things that are not really results, just observations, that the free group targets are decidable using Razbora, which I mentioned just then, and are well known, I suppose, everyone believes it to be so, that abelian targets are polynomial type. So in this talk, I'll just be talking about dihedral group targets. We do this, we show that it's NP complete by starting with a system of equations in this dihedral group and reducing it to the epimorphism problem. And I'll be looking at two cases separately. The n is odd case and n is even when it's not a power of 2, which we can't do, at least using this method. And I'll also be briefly talking about just the general method of epimorphism into extensions with finite quotients. And this is how we do the virtually abelian group stuff. Okay, so this is always a good warm-up exercise for understanding the epimorphism problem. Using von Duke's lemma, which is a way to extend set maps into homomorphisms. Some text there, but essentially to solve epimorphism into finite groups, and we show it's in NP, which is just a non-deterministic polynomial time algorithm. So all we need to do is verify in polynomial time given a correct solution. So on input a presentation, we guess a map from the generators to the finite group. We verify that this set map extends to a homomorphism using the lemma above. And then we just check that the whole group surjects by checking the whole multiplication table. Nothing really complicated, but it is a good demonstration of how it's closely related to the equations problem. So the system equation is just a bunch of variables and constants. An equation without constants just is variables. And this is quite close to a relation, right? So if you have a relation, it's just on a set of generators. You hit it with a set map, it becomes some image of each generator. You view each of these images as a variable, you essentially have a system of equations with no constants over a group. And we verify that these variables, or the images of these generators, are equal to 1 in the new group, then extends to a homomorphism. So given a set of relations, we essentially build a system equation with no constants in the group. Sorry. Okay. So for D2n, what we do is we started with the system equations over D2n, or Dn in a bit, which you'll see. And we try to get to the epimorphism problem. How we do this roughly is we try to identify what I would call a normal form for each dihedral group, depending on whether it's odd or even. And this normal form is not always what you expect, I suppose, which I'll talk about. And then from this normal form, what we do is we try to build a group. This group looks very similar to the dihedral group. And we add some generators to this group and relations so that there's a bunch of generators and relations that just represent these system equations. And then what we want to do is show that an epimorphism exists from this group that we build into a dihedral group, if and only if our original group, our original system equations over our dihedral group has a solution. Right. So we start with the system equations over D2n in this case. I believe this is the odd case. I can't really see the top of my screen, so I think it's the odd case, right? And then we do this normal form thing. So in this case, for the odd case of n, what we do is we conjugate a bunch of our generators by variables. So we can represent each original variable with this long string, which is fine to do. The main thing is, I guess the focus is that these new variables, they're controlled. They don't take values of all of D2n. They only take the value of order 2, the generator of order 2. And then from this, we build a group. I'm going to call it G odd here. And we have this new set of generators in this cow G. And these generators are in bijection with the variables from my normal form equation. And I'll go over this a bit more in a sec, but roughly this is what it looks like. And then we do the epimorphism if and only if statement, right? So the reason we do this group is, that you can see the red generators, they look very similar to the dihedral group. So we want these red generators and relations to go into S and T. So we want A into S and D into T. And how we do this is using the relations on G, which is in blue. We force the G into the image of A, which is S. Okay, so some stuff going on here, right? So you can see G squared is essentially forcing all the images of G to be order 2. And the only things that are order 2 is A, because n is odd in this case. So because n is odd, it's a little bit more simple. And once we control all the generators to do what we want, then we add a bunch of relations, which I've written as lambda of ui. And these relations will be equal to 1 for any homomorphism, if and only if our original system equations has a solution. So that's essentially it, I guess. The main thing is that, yeah, we want to make sure we can separate the G and control the A and D to hit S and T. So this is a little bit straightforward in the odd case, but it's not so straightforward in the even case. Sorry. So in the even case, we actually start with a dihedral group of order n, not 2n. This is not a typo, okay? And what we do is we do the same variable replacement, except this time we're also changing each of our T generator into T squared. And we're actually building a system equation over the larger D2n group, not Dn. So we transform a Dn system equation into D2n. So we're just doubling all of the T generators. The S stays the same. And these new variables form a variable in the larger group. And it's relatively easy to show that a system of equation has a solution from our original equation if and only if these new variables has a solution in this larger D2n, the double size one. And then from there, the process follows almost exactly the same, except the group we build has this nested commutator. And the nested commutator is dependent on what our n value is. So we nest it depending on the number of powers of 2s we have in this n. And the b is an odd value that we stick to the D generator. I'll talk about that a bit more in the next slide. But everything almost works as originally intended. So A is still forced into S. That part is relatively simple. The main thing is because our N has a 2 in it now, it doesn't hit the T straight away. Like it can hit a power of T that's doesn't have GCD 1 with N. Like a little bit complicated, but what essentially means is the image of D without this new generator doesn't hit an element in the dihedral group that will generate all of T. It will just generate a subgroup of T. And this subgroup has a order of B to it. So by adding this new commutator, the nested one, we kind of force it to not hit those elements, because if they do, they'll just be trivial. So then we can't do that. And that's essentially the main trick there. And then once we've controlled for A go into S and D go into T, then the rest of the process is more or less the same, except the main thing is that we have to remember we're working with a larger double-sized dihedral group now, and not the original Dn. Right. So from this, I guess we conjecture a few things. Some of these are a little bit stronger than the others, I believe. So we've shown that, and it's relatively easy to observe, that any group into a abelian group with the promise that the group is abelian, even on a finite presentation, is polynomial time. And we've shown that for any, well, we didn't show for any non-simple finite group, but it is being shown by Kuperberg, and we showed for dihedral group, which in turn gives a result for S3. So basically, the most simple finite non-abelian group is NP hard. So we conjecture that the epimorphism problem from any finite presentation to a fixed group is in polynomial time if and only if the fixed group is abelian. This is a conjecture because we're not able to do it for 2 to the power of n. Sorry, well, n is a power of 2, essentially. At least not with the methods we've used so far, just because we couldn't control where the T goes, right? That I was just talking about. And in some other areas, it's been shown that D8 is roughly a bit more simple than just D2n in general. So that's why we conjecture that the epimorphism from finite presentations to D8 is NP intermediate. And because of this and the above, because D8 is roughly as difficult as any finite fixed nilpotent group, then we conjecture that any finite presentation to a target group is NP complete, or really just NP hard, if and only if the group is non-nilpotent. So then, if this is true, there's kind of like 3 different difficulties of epimorphism problems in finite groups, which separates quite nicely. Okay, now I will briefly talk about the more general problem of extensions. This is going to be very hand wavy and overview, because this is a much more difficult problem, and yeah, I'm going to be doing it in much less time, right? So virtually abelian groups are essentially free abelian by finite extensions. And what we do is we start with just general extensions in our paper. We have some equations problems that are equivalent to that. And depending on what the groups of these equations are over, then we can get to much more simple problems and actually solve these general equation problems. I don't believe are solvable in general without like information on what group it's over. So the overview and the strategy used is we start with attaining an epimorphism into the finite quotient, the Q. And this can't be any epimorphism. It has to be one that's attained from the larger epimorphism, if it exists. This process is NP because it's just the same as verifying a finite epimorphism. And then using this tau, this epimorphism into the finite group, we perform TC transformations on our domain group, the G. And what we want to do is separate a bunch of the generators. We want a bunch of the generators to be in bijection with Q. So I can pick any generator, hit it with tau, and just get another element of Q, get a element of Q. And then we want a bunch of these generators to be only going to 1 in our finite group, in the kernel tau, so that we can check if these things surject the group N, which is the normal subgroup of the extension. And from there, using this presentation, we build a system equations problem. How we do this is a little bit complicated and requires a lot of notation, but in the direct product case, it's a bit more simple. So I'll just talk about that. In the direct product case, we just essentially change each generator into a variable. So for example, if I have a word like x1, x2, y1, x3, I just change it into the variables equivalent to that. And then I have a system equation. And what I want to do is, and I briefly talk about it there. So in the more general case, you have to hit each of these variables with an automorphism. And then depending on the group, it can get really messy, right? So I won't talk about that. Just in the direct product case, I just get a simple system equations directly from my generators. And then I want to check if these generators, these variables have a solution. If they have a solution, then this finite group epimorphism extends to a homomorphism over the large group. And to check if this homomorphism is a epimorphism, we need this additional criteria that the solution of half of these generators, half, not 50%, but just the Y ones, surject the normal subgroup. So this additional criteria is actually a little bit not natural, I guess, looking at it purely from an equations point of view, which is why these problems can be a little bit difficult, because you're not really checking a surjection on all of the generators. You have to get a solution on a bunch of variables and then get rid of a bunch of variables and check if the solution on the subset of these variables surject the group. Yeah, and these are the main resources for this talk. I'll just leave it here for a sec. And yeah, thank you. Any questions?
Thank you, Jerry. Does anyone have any questions? So I guess my question is, Roman first.
Yeah, I guess because one of your conjectures was that the problem at D8 is NP intermediate, right?
Yes.
So that would imply NP isn't equal to P. Do you think
Yeah.
this is a good avenue to tackle that problem, or do you think, oh, if they prove it somewhere else, we can use this to prove?
I think this is probably a conjecture that will not be proved. If that makes sense. So I guess I don't really understand this very well. The collaborator Armin understands these groups much better than I do, and I guess the main thing is there's a bunch of, I think it was using automatons to show these D8 problems, and nilpotent dihedral groups are in general more simple. That's my understanding. That's far as my understanding really goes. So I was a little bit, I guess, shocked as well to say, oh, okay, I don't, maybe it's not NP intermediate. Maybe we could actually show it's NP hard, but yeah, we can't do it yet, at least not with the tech that we've used so far.
Thank you.
Yeah, I guess NP intermediate stuff is always a bit, like.
Yeah, I was wondering whether there's like a underlying assumption there of like, oh, if this problem is NP intermediate, then that one would also be.
Okay, right. Yeah, probably, but I don't know it well enough, really. Yeah.
All right. Thank you.
So what goes wrong when you have this sort of dihedral group of just a power of 2 order?
This
Because
is
your
probably a good
statement,
slide.
you
Yeah, so we just can't. So we want D to go to T essentially, right? Yeah, so we want to make sure D goes to T, but this commutator won't work in the case where N is a power of 2, because then C is just 1. So obviously this commutator doesn't work, but we would have to try to look for another trick. And we would also have to try to find this normal form thing. I don't know if you can see my cursor, but
yeah.
so the
Okay.
first thing is we have to generate a equivalent system equation. And then we have to make sure using that system equation, we can control where A and D goes so that G just represents the system equation. And currently we haven't worked out a way to control where G goes, in the sense that we can't find a strict way to get G to not go into any part of T. Because if it hits some part of T, then it can help generate all of T, then D doesn't have to hit all of T.
Okay.
Makes sense? Yeah. So then
Yeah.
if we can't control where G goes, then the system equation doesn't necessarily extend to a bunch of relations that have to go to 1.
Okay, cool.
Yeah.
Thanks.
Yeah, so we just can't build a group that gives an if and only if statement.
Yeah. Does anyone else have any questions? If not, we'll thank Jerry again.
Cool, thanks guys.
Thanks, Jerry.